is our AP Chemistry Chapter 7 lesson video part 2. And so in this video, I'm going to cover section 7.4 through 7.6. Alright, so 7.4 we're going to focus on ionization energy first of all. Okay, so if you watch the part 1, we discussed effective nuclear charge, and we discussed that when we are talking about trends, we need to focus on effective nuclear charge and the distance from the nucleus. Okay, those are the two things that Coulomb's law discusses. Alright, so whenever you're trying to explain a trend, you need to focus on one or both of those. It depends on which one matters. So the ionization energy of an atom or ion is the amount of energy required to remove one electron from the ground state of the isolated gaseous atom or ion. So we are trying to remove an electron. So notice the values for a given element increase as successive electrons are removed. So first ionization energy is lower than second, which is lower than third, and so forth. This trend exists because each extra electron is being removed from an increasingly positive ion. So like for sodium, our first ionization energy is only 498. Our second one is 4,560. And every time we try to remove another electron, the ionization energy becomes larger. And that's of course because the nucleus is still just as strong. So as you take away electrons, the nucleus has a stronger pull on the remaining electrons. Now, what you may notice, and this one points it out, but we'll look at it on the next one, is that it increases every time, but sometimes you'll all of a sudden see a huge increase. Like for example, with aluminum, it's 577, 1815, 2740, but then all of a sudden it jumps up to 11,000. Like, why is there that giant jump? Well, that's based on whether you're trying to remove a valence electron or a core electron. So there's a sharp increase in the ionization energy that occurs when an inner shell or core electron is removed. This is the reason that only valence electrons are involved in bonding. So for example, if you look at the periodic table, magnesium, wait, is that even on here? Okay, magnesium, it has 2 valence electrons. So what that means is my first and second ionization energies should kind of be normal in size, but the third one I should see a much larger increase because I'm removing a core electron. So let's look at magnesium. So we have about 700, then we have about 1,400, then we jump to almost 8,000, is 7,700. So that's why at the third ionization energy we have that huge jump, because now we're removing a core electron. So if you look, if we pick something else like lithium, lithium has 1 valence electron. So I should see a huge jump just between the first and the second, which I do. The first one has 520, the second one has 7,300. Okay, and so that can let you know how many valence it has. So for example, let's look at nitrogen. Nitrogen has 5 valence electrons. So we have 1,400, 2,800, 4,500, 7,500, 9,400, and then it jumps to 53,000. So why does it jump there? Because we've removed all 5 of the valence electrons, and so now the 53,000 is a core electron. So if you know ionization energies, you should be able to tell how many valence electrons something has. Alright, so it says, based on the locations of sodium, calcium, and sulfur, predict the one with the largest second ionization energy. So y'all, that's where you have to be careful on these. You need to look at which ionization energy they're asking you about. Are they asking you about the first one and we're just removing one? In that case, you can look at your trends. So ionization energy decreases going down and increases across. But if they ask about a second or third or so forth and so on, that's when you really need to start focusing on valence electrons. Okay, so it says who has the largest second ionization energy? Well, let's look at our valence electrons. So sodium has 1 valence electron because it's in group 1. Calcium has 2 valence electrons because it's in group 2. And sulfur has 6 valence electrons because it's in group 16. So I'm looking at second ionization energy. Well, sulfur has 2 valence electrons that can be removed. Calcium has 2 valence electrons that can be removed. Sodium only has 1. So once I do the second ionization energy, I'm removing a core electron at that point. So it would be sodium because now you're removing a core electron. Okay, core electrons have much higher ionization energies than valence electrons. Alright, so our answer is sodium. So then it says, which will have the greater third ionization energy, calcium or sulfur? So pause it, try it, and now we'll look at it together. Okay, so I'm looking for the greater third ionization energy. So remember, let's look at those valence. So calcium's in group 2, so it has 2 valence electrons. Sulfur is in group 16, so it has 6 valence electrons. So we're going to third ionization energy. So I have at least 3 valence electrons I can remove from here. But calcium only has 2. So once I try to remove that third one, that's going to be a core electron or an inner shell electron. So it would be calcium for that one. So hopefully you got that right. Alright, so let's just talk about, in general, ionization energy trend as we go across and down. Normally we discuss first ionization energy. So ionization energy generally increases as you move across a period. This trend occurs because moving across the periodic table, Z effective increases and the radius of the atom decreases. So more energy is required to remove an electron. So y'all, if you're trying to explain this trend, you need to focus on that stronger nucleus, that Z effective. Okay, so the nucleus gets increasingly positive as we go across, but the electrons just keep being added to the same energy level. Okay, so that stronger nucleus can pull them closer. Well, if the pull on the nucleus is stronger, then it's going to take me more energy to remove that electron. Alright, so it increases going across, and then of course it decreases going down a group. So ionization energy decreases as you move down a group. This trend occurs because electrons are farther from the nucleus since they are in larger energy levels, so the energy required to remove one is lower. So remember, as we go down the periodic table, we're getting larger and larger energy levels. The farther an electron is away from the nucleus, the easier it is to remove because there's less attraction. Remember, Coulomb's law is based on the strength of the nucleus, or Z effective, and distance from the nucleus. When you go across the periodic table, normally we focus on Z effective. When you go down the periodic table, we normally focus on larger energy levels that are farther from the nucleus. So make sure when you're doing explaining, though, you always focus on this. So what's going on in the D block? So first of all, what is the D block? Well, if you remember from electron configuration, here's S, P is over here, here's D, and F is down here. So the change in ionization energy is greater in the S and P blocks of the periodic table. The energies only increase slightly across the D and F blocks. So y'all, that's a common thing on the trends, is there is less change across a D and F sublevel than there is across S and P. And so I know this is probably hard to see in the video, but this is just showing the height of each element, and so as you're looking across D and F, you just don't see much difference in them. Okay, but like I said, that's a common factor in the trends across the D and F. So it says, arrange the following atoms in order of increasing first ionization energy. So we have Ne, Na, P, Ar, and K. So first, let's draw like a fake periodic table real quick so that we can get all these listed on here. Alright, I know I'm doing ionization energy, so I'm going to go ahead and put myself a little reminder that it decreases going down and it increases going across. Alright, so we have Ne, so we're looking at about right here. Alright, we have Na, which is just right down here. We have P, which is about right here. Alright, we have Ar, which is right under Ne. And we have K, which is right under Na. Just like that. Alright. Just making sure I'm at the right spot and I haven't passed where I'm supposed to stop my video. Alright, so whenever you have multiple elements in different periods and groups, I like to focus on one period at a time. It's easiest to focus on the up and down first and then worry about the cross. Alright, so we're putting them in order of increasing. So remember, you gotta always check what they're asking. Increasing. So we want lowest ionization energy first. Well, if you look, what happens as we go down, it decreases. Okay, so neon is in the second energy level. Sodium, phosphorus, and argon are in the third, and potassium's in the fourth. Okay, so I'm not worried about the second or third right now. Potassium's the lowest. It has the most energy levels, so it's going to have the lowest first ionization energy because, of course, it has the most energy levels. Alright, so next, I'm not going to focus on the fourth or the second energy level. I'm just going to look across the third. Alright, so I can see it increases going across, so I'm going to keep these in order. So it'll be Na, P, Ar, just like that. Alright, and so then last I just look at my highest one, that is neon. So then I put neon last, just like that. Okay, so like I said, y'all, just focus on one row at a time. Don't try to compare all of them or that gets a little confusing. All right, so hopefully you got that. And you'll have a periodic table during the AP exam so you can identify where all the elements are and everything. All right, so it says which has the lowest first ionization energy, B, A, L, C, or Si, which has the highest. Okay, so pause the video, you try that one. I'll assume you've done that, and then we'll look at it together. Okay, so first let's find them. All right, so we have B, A, L, C, Si. So that's how they are on the periodic table. Okay, so remember, we're looking at first ionization energy, so it's going to increase across, decrease down. All right, so it says which has the lowest first ionization energy. Okay, so remember, look up and down first, so it decreases going down. So that means these would be the lowest. It increases across, so that means AL is going to be the absolute lowest. So my lowest would be AL because it decreases going down, so I can cover up these two, but it increases across, so it's AL. Then it says which has the highest first ionization energy. Okay, so I block off my bottom two because I know it decreases down, so these are going to naturally be higher. And then out of these two, it increases across, so it would be carbon, just like that. Okay, so like I said, y'all, just try to focus on one at a time. I always kind of look at up and down first, and then I kind of use across when necessary. All right, so electron configuration for ions. So we did electron configuration in chapter 6, okay, but we're just going to go back to it real quick. So when electrons are removed from a cation, they are removed from the highest sublevel in the highest principal energy level first. When electrons are added to an anion, they are added to the last partially filled orbital or the next sublevel. Okay, so like when we have fluorine, we have 2p5, they just split up the p's here, not a big deal, 2p5, so when fluorine becomes fluoride and has a -1, we add that 6th electron to that 2p. That's all that's happening. Okay, so let's look at some of these. So it says write the electron configuration for the following. It didn't specify, so I'm just going to do standard. Okay, you could do arrow if you wanted to. I wouldn't do that though. I would waste my time with that. All right, so we have calcium with a +2 charge. So first, let's just do the electron configuration for calcium. So I'm going to assume you kind of already remember how that works. All right, so we have hydrogen. So we have 1s2, hydrogen, helium. Lithium is 2s2. Boron is 2p6. Sodium is 3s2. Aluminum is 3p6. And then potassium, is 4s2. So that'll get me all the way to calcium. All right, but it says it's calcium with a +2 charge. +2 charge means it loses 2 electrons. See, a lot of y'all, you want to add 2, but it's going to lose 2. Remember, it's negatives, so everything seems backwards. So we have to remove from the highest sublevel. So we remove that 4s2. So your answer should just end with 3p6. All right, so let's look at cobalt with a +3 charge. All right, so cobalt, we're starting at hydrogen. So we have 1s2. Lithium, 2s2. Boron, 2p6. Sodium, 3s2. Aluminum, 3p6. Potassium, 4s2. And scandium, we're at 3d. We don't need all 10 because we're going to stop at cobalt. 1, 2, 3, 4, 5, 6, 7. So I get 3d7. Now this is where if you're watching my electron configuration video for chapter 6, I mentioned that I make y'all rearrange. But on the AP exam, they don't. This is the reason why I'm still going to make you. Okay, because the thing is, what does a +3 mean? It means it loses 3 electrons. You have to take them from the highest sublevel. Well, if you write it like this and leave it like this, you're likely to say, okay, well, I'm going to take 3 out of there and it's going to end in 3d4. Sorry, I'm just making sure it's 7. 1, 2, 3, 4, 5, 6. Okay, I felt like I miscounted the whole time I was talking. I guess I could just get mine out. I have my answers pre-worked out. I just wasn't looking. All right, so you would be likely to do something like this. But the thing is, y'all, you need to whoops, sorry, that was a 7. You need to rearrange first. Okay, so I'm going to put 3d7 and then 4s2. Because if you'll rearrange, you'll remember that 4s is higher energy. So if I need to lose 3, I can get rid of 4s2, but that's only 2 of them. So I still need to get rid of 1 from 3D, so it would end up with 3D6. Okay, so like I said, that's why I will make y'all rearrange. I don't know about other teachers if you're not in my class watching this, but that's why you should, so you don't forget and take them out of the wrong sublevel. All right, so last one is S with a -2. So let's just do S normally first. So I have hydrogen, and then lithium, and then boron, and then sodium, and then aluminum, but we're stopping at S, so it would be 3p4. But it's sulfur with a negative charge. It's a sulfide ion, so that means it gains 2 electrons. So instead of ending at 3p4, it's going to end with 3p6. All right, so hopefully you remember doing this from honors. If not, there's a refresher. All right, so pause it. You try these real quick, and then we'll look at them together. All right, so I'll assume you've already done it. All right, so we're doing gallium first. Okay, so I'm going to start at hydrogen, hydrogen, lithium, boron, sodium, aluminum, potassium, scandium, let's see, gallium. So we end with 4p1. All right, just like that. Now, like I said, I know on the AP exam, they do not expect you to rearrange. However, I expect you to rearrange. Okay, because again, what does +3 mean? It means we're going to lose 3 electrons. So you're likely to say, okay, let me get rid of 4p1 and take 2 out of 3d. But 3d is not the next highest. You need to rearrange these. Okay, so it'd be 3d10 for S2. So now when I need to remove 3, I'm going to remove 4p1 and 4s2, just like that. Okay, so hopefully you rearrange like you're supposed to. All right, so next one is chromium with a +3. Okay, so let's do chromium first. So I have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d for chromium, 1, 2, 3, 4. 3d4, just like that. All right, so y'all, remember, we have to remember to rearrange. Otherwise, you're likely to mess up. All right, so I end up with 3d4, 4s2. And so what does +3 mean? It means I'm going to lose 3 electrons, just like that. Okay, so I'm going to get rid of 4s2, and I'm going to get rid of 1 from 3d. So I'll end with 3d3 for that one. All right, so hopefully you got that one right. All right, and then last one is Br with a -1. Remember, if it just says positive or negative, that indicates a 1. All right, so I'm going to go to bromine. So I have 1s2, 2s2. I'm going to assume you know the order at this point. 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Is that where bromine is? Yes. All right, so again, y'all, this one, it doesn't actually make your answer wrong if you don't rearrange. However, y'all, just do it every time. Okay, that way you don't forget. So let me put my 3d10 first and my 4s2. All right, so this means it's going to gain 1 electron. So instead of ending at 4p5, it should end at 4p6, just like that. All right, so like I said, hopefully this is all coming back to you from Honors Chem, because we did all this. And remember, electron configuration was y'all's strong area, so hopefully it's coming back pretty easily. All right, so moving on to 7.5. So now we're going to talk electron affinity. Electron affinity is one of the weirdest trends just because it's not very trendy, as in it's barely a trend sometimes. So I don't see a lot of questions about electron affinity usually. So the energy change that occurs when an electron is added to a gaseous atom is called the electron affinity. It measures the attraction of the atom for the added electron. So you may think, wait a minute, this sounds really similar to electronegativity, which is the ability of an atom to gain an electron, and it's related to it, okay, but the difference is the energy change that occurs when that electron's added, whereas electronegativity is the ability of it to gain an electron. Now, most of the time, we just kind of say the trends are the same because they are kind of the same, but like I said, electron affinity is just not a very strong trend. So for most atoms, energy is released when an electron is added, of course, because an electron's negative and a nucleus is positive. So if we can bring them closer together, that releases energy. Electron affinity does not have a consistent trend going across a period. it does overall increase as you move across. Okay, so that's why I say we kind of just follow electronegativity, which also increases and decreases. So as you go across, you can see it's just crazy and odd, but overall it's increasing. But here's the thing that we say. When we say it's increasing, we mean it's getting more negative as we go across. All right, this trend occurs due to the increased Z effective in the smaller atomic radius. So remember, we talked about when you explain a trend going across, you need to focus on Z effective, or your nuclear charge. The electron affinity slightly decreases as you move down a group, and again, that's because the energy levels are farther from the nucleus. All right, so remember, when you're explaining across, you want to focus on Z effective. When you're explaining down, you want to focus on larger energy levels. All right, so 7.6. I don't actually remember if I said I was covering this one. Let me check real quick. Oh gosh. All right, yes I am. Wow. All right, probably should edit that out, but I'm not going to. All right, so metals, nonmetals, and metalloids. So we learned about these in honors also. So your metals are group 1 and group 2, not hydrogen. All of your transition metals, 3 through 12, all the lanthanides, actinides, and then everything up under the stair step, but not touching the stair step. Okay, so you can see it kind of forms this little triangular area. Your metalloids are what touches the stair step, except for aluminum. I'll tell you, PO, I see both ways, but most of the time nobody's going to ask about that. AT, I also see both ways. Some people, they just kind of stop right here with the metalloids. All right, and then your nonmetals are to the right of the stair step and hydrogen. So what are some properties of metals? Well, they're solids at room temperature, except for mercury, that's a liquid. They have low ionization energies, which means they form cations, but you know that. That's where our positives are. Here, let's go back. Remember, we have +1, +2. This whole area is positive. It can just have more than one charge, +3. Okay, and even under here, even though we get to the plus or -4 area, these are still all positive. Metals are oxidized. Oxidation is the loss of electrons. Well, that makes sense because they're cations. In reactions, they're malleable, ductile, good conductors. They form ionic compounds with nonmetals. And then metal oxides are basic. Okay, so obviously they're going to bond with a nonmetal because nonmetals tend to be negative. So that's where we get our ionic compounds from. So, sample exercise 7.8, it says, would you expect scandium oxide to be a solid, liquid, or gas at room temperature? All right, so y'all, if you look, it says that they form ionic compounds with nonmetals. Well, one thing we know about ionic compounds is, of course, they are solids at room temperature. Okay, so once I see this is a metal and this is a nonmetal, I can say, hey, this is going to be an ionic compound, which tend to be solid. So that's how you would know the answer to that one. All right, so solid for that one. Then it says, write the balanced equation for the reaction of scandium oxide with nitric acid. Okay, and it tells me scandium has a +3 charge. All right, so we have scandium oxide, so it told me scandium's +3, oxygen's -2, so I'm going to cross that 2 and that 3. All right, and it's reacting with nitric acid. So if it ends in acid, it starts with H. H has a +1 charge. Nitric comes from nitrate, of course, because I ate something icky. So nitrate's NO3 negative, so I don't need to cross anything. And so then we just need to look at what's going to happen here. Okay, so y'all, on this type right here, if you look, like we have these paired up and these paired up, and so what we're kind of going to do is do like a double displacement reaction type thing. Okay, so now SC is going to bond with NO3. So I bring over my SC +3, my NO3 negative, and I'm going to cross that 3 down. Now H is going to bond with O. So y'all, when H bonds with O, it's just going to make water, H2O. All right, so we get our H2O. And then, let's see. Oh, we are supposed to balance it. Oh, it says balance it. That's why I was grabbing mine to see if I balanced it. All right, so we have 2 SC, 1 SC, so I'll put a 2 here. All right, we have 1 NO3, but here I have 6 NO3s, so I need a 6 here. I have 6 H's and 2 H's, so I need a 3. And then I have 3 O's and 3 O's. All right, and so that's all you have to do for them. So don't forget your types of reactions, okay? We know synthesis, decomposition, single, double. Like once you see that both parts are paired up, that should make you think double displacement. All right, so here's one for y'all to try. It says write the balanced equation for the reaction between copper 2 oxide and sulfuric acid. Okay, so y'all try that one, pause it, I'll assume you've done that, and now we'll look at it together. All right, so we have copper 2 oxide, so copper 2 means positive 2, oxide has a negative 2, so I don't need to cross any of that. Sulfuric acid, if it ends in acid, it starts with H. Sulfuric came from sulfate, which is SO4, negative 2, so I cross that 2 down, so I get my charges balanced. All right, so remember y'all, we're just swapping our positives. So Cu is now going to bond with SO4. So it's positive 2, negative 2, so I don't have to cross anything. All right, and now H is going to bond with O, and so I'm going to make H2O. All right, and so it says write the balanced equation. Whoops, that should say balanced. So I have Cu, Cu, SO4, SO4, 2 H's, 2 H's, an O, and an O. All right, so hopefully you got that one right. Always make sure you know how to write equations. I like to ask those a lot. All right, so we talked about metals. So nonmetals are the opposite. They tend to be gases at room temperature. They have high electron affinities, so they form anions. So that means it's very favorable for them to gain electrons. Because of course they're trying to be like a noble gas. They want to have stable 8 valence electrons. Nonmetals are reduced, which means they gain electrons. Oxidation is loss, reduction is gain. They are brittle, poor conductors. They form molecular compounds with other nonmetals or ionic compounds with metals. And then nonmetal oxides are acidic. So it says, write the balanced equation for a reaction of solid selenium dioxide and the following. So we have water, and then we have aqueous sodium hydroxide. All right, so we're writing the balanced equation for both of these. So we have selenium dioxide, so I don't need to do anything with charges because it tells me exactly what it is, and water. Okay, so I have selenium dioxide and water. Now on this one, I would not expect you to know what was going to form, and I don't think they would on the AP exam either. I think they would tell you what it forms, because this isn't like a single or double. This is actually synthesis. Like they're both just going to come together, and you're actually going to make this right here. Because SeO3 is a polyatomic ion, and so again, I don't think they would expect you to know that's what's going to form. But let's go ahead and balance this thing. So we have Se, Se, we have 2 H's, 2 H's, 3 O's, and 3 O's. All right, so let's look at our next one. So here we have selenium dioxide, so we're still starting with SeO2, and sodium hydroxide. So sodium is Na, hydroxide is OH, positive and negative, so that all cancels out all nice and good. All right, and so for this one, again, because you're kind of favoring something similar to this, making this polyatomic ion, I don't think they would expect you to know how to do this on the AP exam. Remember, these questions I pulled from the textbook. The textbook knows you can use resources while you're using the textbook. Okay, so in this case, the Na is going to bond with the SeO2, but it's going to form into this polyatomic ion. Okay, so we get Na positive and we get SeO3, which is -2. So I need 2 Nas. And so again, I don't think that they would expect you to know that that was going to happen. All right, and so then, of course, we're going to have H2O. All right, so let's balance this thing. So I have Se, Se, 1 Na, 2 Nas, so I'll put a 2 here. I have 2 H's, 2 H's, and 2 4O's, 3 4O's, just like that. Okay, so like I said, y'all, when you're watching this, don't stress out about, oh my gosh, I wouldn't have known those were the products. Okay, nobody expects you to know those are the products. Okay, I just do the ones out of the book, whether it's something you would see on the AP exam or not. All right, so pause it, y'all try this one, and then we'll look at it together. So it says, write the balanced equation for the reaction of solid tetraphosphorus hexoxide with water. Okay, so we have solid tetraphosphorus hexoxide, so I know that's P4O6 and water. Okay, so again, y'all, on this one, they're not going to expect you to be able to come up with these products. Okay, but for this one, you end up getting phosphorus acid. Okay, and the whole reason that we're doing these is because of, hang on, I'll come back, how it says non-metal oxides are acidic and metal oxides are basic. So it's just showing, whoops, I'm not on the right one. It's just showing you it is acidic because it makes an acid when it goes into the water. Alright, but it was a balanced equation, so we got a balance. We have 4 P's, but here I only have 1, so I'm going to put a 4. Here I have 2 H's, here I have 12, so I'm going to put a 6. Here I have 6 plus 6, which is 12 O's, and I have 12 O's, just like that. Alright? Alright, so last is metalloids. Metalloids have properties intermediate between those of metals and nonmetals. So it might be shiny like a metal, but brittle like a nonmetal. And that is it for this video. Alright, so hopefully the properties of metals, nonmetals, and metalloids, you should have only seen a couple that we didn't discuss in honors. And then we've done the trends in honors and the electron configuration of ions. So again, if you're struggling with any of that, go back and focus on my chapter 5, 6, and 7 lesson videos in honors. That's where all of this is kind of housed.